Thank you. It's interesting to see so many people who are feeling unnecessarily good and looking for a downer. You have come to the right place. So this is When to Give Up and How. I'm Björn Fahller. I want to start this by saying that this is a talk based on my personal experiences, and even though I have been in this field of software development for quite some time, I have not worked in every possible field of software development, so there is definitely a chance that you are working in areas where some of the things that I say may not apply. And in fact, it's likely that some of you are working in fields where some of the things I say would be illegal for you to do. There are regulations in some places, or so I'm told. But yeah, so this is things that I have learned through the years. Start the timer. My experience comes largely from Net Insight. I work for Net Insight in Stockholm. We make network equipment like these things. A heck of a lot of CPUs in these pictures. Every plug-in board has at least 2 CPUs and a couple of FPGAs. So, yes, much. I said I would speak from personal experience, and you can argue that this talk has its root 27 years ago. It was the summer of 98, I think it was 98, maybe 99, but probably 98. I was writing a document, and the common wisdom at the time was save often, because this word processor is crashing a lot. But if you save every paragraph or something, you will only lose the last few minutes of your work when it crashes. So it's not a big deal. So I was writing a lot. I had an unusually good flow. I usually find it difficult to write documents, but in this case, I had a good flow. I was writing a lot. I was adding illustrations to clarify what I mean with things. But after a while, the word processor started behaving oddly. For example, when I added an illustration, it liked to default place the image across a page break. That is a bad default. And sometimes it just started letting paragraphs go outside the page boundary, and sometimes it just changed to a completely different font for no reason. And none of these issues really stopped me, but they were annoying. It took just a few seconds to correct them, each and every one of them, but it was annoying, but I kept working. And early afternoon, sometime, I decided that, no, this is too flaky, I'm shutting down. And then I can start the word processor again from a clean slate. Except I couldn't, because the file was corrupt. So instead of losing the last few minutes of my work because I saved often, I lost the whole day's worth of work because the file couldn't be read. Had this word processor crashed on me, I wouldn't still be angry 27 years later. I would just say that this was a stupid program that doesn't work correctly. But now with this case, this is bad. I mean, crashing is bad, but corrupting my data, that is worse. So now you know why I'm here. I want to set some terminology for the purposes of this presentation. So when I talk about a bug, I mean that the program does not behave correctly due to flaws in the logic itself. But we have also disappointments, things that happen that are outside of the desired outcome. This can be things like malformed input, disk full, out of memory. You may or may not choose to act on these. How many handled properly that you fail to allocate memory? How many handles properly a disk full situation? For the YouTube, I see 4 very reluctant hands. I saw no hands on the memory. So depending on what kind of program you write, these can be super important to deal with or actually not something to bother with. Error handling is program logic that deals with disappointment. Do not treat bugs like as if they were disappointments that you try to programmatically deal with. So one of my favorite examples of this is the POSIX function close. Close is a file descriptor. If something goes wrong, it returns a negative value, and you look at the error variable to see why did it fail. Did it fail because the disk was full? Did it fail because whatever? But the error code e-inval has exactly one reason to occur, and that is because the file descriptor you passed is not a file descriptor. The operating system does not know about any file with this value. So what is a good error handling strategy here? Crash, yeah. Close another file descriptor? Probably not. You can log, I guess, but nobody reads these logs. So So this talk is about bugs, in case you hadn't noticed. So how can a program know that it has a bug? Well, a function can see that it has been called with an invalid argument. That makes sense. It can see that it has been called in an illegal state, or that a caller can see that a return value or an exception thrown is outside of what is specified. Well, and of course, also, a function can see that data is somehow inconsistent or invalid. Now, I've gotten into arguments with people about the last point, and they say that yeah, but we don't use raw pointers and pointer arithmetics, etc., in our programs. That is non-issue. That is not what I'm talking about. If you have some kind of state at all, and you have some constraint on the state, you can find yourself with a state that is outside of the constraints. That is a bug. For example, you have a program that has one variable as its state. It's an unsigned integral value, and you have a constraint that it must be less than 100. But in some function, you suddenly realize that this variable has the value 101. There you have it. Inconsistent data or invalid data. It's not allowed. Now, as far as I can see, there are 3 possible ways to get into this situation. You can have ionizing radiation that randomly flips bits. You can have faulty hardware that gets a stuck bit somewhere. That can happen. Or you have a bug. Unless you are writing software for use in space or cleaning up nuclear disasters, I would say that bugs is by far the most likely cause. So, in order, however, to see that you are outside of spec, you need to define what actually we mean when we say legal, valid, consistent. If you don't specify this, how can you say that you're outside what is legal or valid? So, what to do? Well, in my experience, this is a by far most popular technique. If you don't define what's right, then you don't have to deal with what's wrong. Problem solved. Everything's fine. But what if we don't want to be that bad person? Say we have this function, and we notice that it has been called with a null pointer, and that is not allowed. So and it crashes, so that is bad. So we make this change and say, hey, if it's called with a null pointer, just return, do nothing. Or if this callback is called in an invalid state, don't do anything. This is hiding the problem. This is not solving the problem. I call these counter bugs because they are there to make the real bug not appear. And when you do this, you make it much less likely for yourself to find the underlying issue, to do something about it, because now it's more difficult to trigger it. Now, I'm not saying that this is never, ever the right thing to do. It can actually be. But you only know this if you've done your homework. You look at all the possible call paths to these functions and see that it is okay to do nothing. And then you make an update to the documentation of the function and say that if called with null pointer, it's a no-op. I have yet to see a developer do that, a developer who has written this code. To write code like this without doing this kind of analysis makes me quite upset, because it just makes it harder to find what is actually going on. As a developer in this situation, you have two goals to solve. One is to cause as little damage as possible, whatever that is. Sometimes doing as little damage as possible is to crash so that you don't corrupt data. Sometimes it's something else, it depends. Maybe it actually is the right thing to continue running and doing something that is wrong. That is scary, but it can actually be the right thing to do. But you also need to gather information so that you, the developer, can figure out what is the underlying issue, where did the bug come from, so that you can fix it. And sadly, these can be in conflict. And that is just, unfortunately, the way things are. So, how about assert? Anyone uses assert? Half the hands, roughly. So let's change it this way instead. We assert that if it was called with not bad sound, if the callback is called in an invalid state. What does this mean? Well, assert does one of absolutely nothing or calls abort. So this is a bit scary, but that is the choice we have. Whether assert is active or not is controlled at compile time whether you use the ndebug macro or not. So you can control it per source file if you want them active or not, but it is controlled at compile time. When assert is called, when assert is triggered, it calls std_abort. It usually it crashes your program, terminates execution. It usually does so with a message, often often a stack trace. If you're on a Linux-like system, you probably get a core dump. I will talk about core dumps later. They are super useful. So when you get information from a triggered assert, you often have really good chances of hunting down the bug. That is good. But of course, it took a crash to get there, so that is not good. Many companies have their own assert macros to offer more fine-grained control over when to abort. So, for example, to enable or disable at runtime, or to partition your code into different parts and say that I want the assertions active in these parts of the code, but not in those. Or even have different levels of paranoia, like how expensive checks are you prepared to make. I really don't like this microphone. What about contracts? Are you interested in contracts? Yay, a few hands, but they are very, very enthusiastic. Contracts are a way of expressing what to expect. So you can state on a function a precondition saying that in order to call this function, you must promise blah, blah, blah. And if you fulfill that promise, then the function can itself promise that then I will deliver blah, blah, blah. This is useful. This is great. This is one of those really big things coming to C++ 20. Here's some random dude talking about that at an international programming conference, and then contracts were scrapped from C++ 20. My best talk that went for nothing. But they say it's coming to 26. Touch wood. I hope it will. Programmatically, you write like this. The function has a precondition. This is by the current draft standard of C++, by the way. Heavens knows if it's going to change. But the way it currently looks is you write that p must not be a null pointer. Or in the case of the callback, the precondition is that it must be in a valid state. This offers so much better visibility in terms of expectations from a function, in my opinion. And also, since this is part of the language itself, it means that third-party libraries will, over time, start using these. So you have the same mechanism everywhere. Currently, if you roll your own company assert macro thing, a third-party library probably doesn't use that macro. But this is good. As I understand the latest reading I did of the draft standard, it may have changed after I read that. It is very unclear of what we can expect from implementations regarding support for writing your own custom violation handlers. A violation handler is what is called if a contract is violated. The phrasing, if I remember correctly, was something that it is implementation defined whether custom violation handlers is supported, and if it is not supported and you provide one anyway, the program is ill-formed, no diagnostic required. I really don't like that last part. Let's hope it has been changed. Otherwise, the contracts suffer from the problem that it's program-wide. You cannot turn on and off per translation unit. If we have access to implementing our own custom violation handlers, then I guess we could implement a violation handler that can see, oh, we are in this part of the source tree, therefore I choose to return and do nothing, or to log, or to abort, or whatever. But at this moment in time, I think it's unclear. This was fun. This was a number of years ago. We had a very strict policy of the program must never crash, which sounds good. And we really didn't have a very good chances of achieving that, because the system did not have a memory management unit. We worked directly on the physical addresses. Null was perfectly fine, except that there were so many who wanted to use it. So it stores something there, but when you want to read it back, it's somebody else's data. And of course, sooner or later, somebody wrote to null with a large enough offset to overwrite the interrupt vector, and then things started getting very interesting. And the system wasn't stable at all. It crashed a lot. And when analyzing the crashes, we could really just see that, yeah, the data is complete, utter nonsense. That there is no right thing to do here at all. It's just crazy. And it was impossible to understand what we need to do. Where did the problem originate from? Everything is just random bits. So a colleague and I, we guerrilla added asserts a lot. To begin with, the obvious ones, do not access the null pointer, neither for reading nor for writing. And I will not lie to you, the behavior the next couple of weeks was not great. It crashed a lot. But now we crashed with actionable information. We understood why we crashed, so we could fix these. And after a couple of weeks, a month, something like that, I feel really sorry for the guys who are going to try to launder the audio for the recordings. After a couple of weeks to a month, something like that, the system was stable. We couldn't anymore provoke crashes because we had found the bad situations. I'm sure there were still places left, but it was not something that just happened regularly by any means. So it is kind of weird, sort of in a way, that we added code to deliberately cause premature termination, and that helped improving stability. But that's how it works, or how it worked for us at least. So here's the thing: to be able to fix a bug, you need information about the bug. So you need to gather information as much as possible so that you can learn where the bug originated from to fix it. And this one is counterintuitive, the second point. Terminate as early as possible. If something's going to fail right away. Don't do a lot of extra work and then fail. Because when all this extra work will just corrupt the data that makes the analysis more difficult. If you're going to crash right away. The sooner the better. So, can we do better? This one is interesting. The very first job I had, my first full-time job, it was actually before going to university. I was working for Ericsson with their AXE digital telephone exchange. Note the word digital, because the predecessors were analog and electromechanical. The AXE phone exchange was designed in the early 70s, first deployment in 76. One of these can serve a city. The central processor is something that handles things like billing, monitoring of the system, and subscriber services. For the first time, a subscriber could request wake-up calls or call forwarding and such things, since these were now computerized, digital. Whoa. Typically stores 10 to 15 words of data per subscriber, so big data here. The central processor was duplicated for redundancy. And in the middle there we have the MAU, the maintenance unit. The role of the maintenance unit was to monitor the two CPUs. So it continuously monitors for things like parity errors and such. And this is curious. No one would ever design like this today. But the two CPUs were in lockstep, cycle by cycle, identical, running exactly the same thing. And the MAU compared the address line and data lines to see that they did the same thing. And if it found out that they differed, they ran some short diagnostic program to try to figure out which one is the faulty. And the faulty one is shut down. An alarm is raised, and the phone exchange continues to run on a single CPU. Early 70s. How often did the CPUs fail? I have absolutely no idea. And this was a hierarchical structure, so that outside of the the central processor, you had regional processors. There were thousands of regional processors. And they could work even if contact with the central processor was down. And they too were duplicated, but for different reasons. These run individually, and they take care of half the job each. Not for load sharing, but for damage control. If one of them dies, then only half the work is lost. And when one is shut down, then the responsibilities of that one is transferred to the other CPU. So they are continuously monitored for faults, but we don't have this redundancy where we check them cycle by cycle. It's more like seeing, oh, seems to be a parity error or a trap or something. And when a fault is detected, like I said, the work is moved to the other one and a restart is attempted. It could, for example, attempt to reload the software and such things. And the thing is here, the phone calls that were running, they were completely independent of the CPUs. The CPUs could be needed when making a phone call. But once a phone call was established, it was running. CPUs weren't involved at all. And in the steps outside of this, there are no CPUs involved. It's only hardware. So the bits that I was working on at the time was, I forget what it stood for, ETC, external subscriber terminal or something like that. It was a single board for ASICs and some TTL circuitry. And if it had power, it could run on its own. So it could serve 30 subscribers, so a village. If connection with the regional processors were down, it could still make phone calls within that village. Still establish phone calls within that village. The autonomy of the parts makes this design super fault tolerant. You can have so many bits and pieces that are shut down and the system still works. Degraded, yes, but it works. But curiously, all fault detection is aimed at hardware malfunction. As far as I know, there was absolutely no attempt whatsoever to discover if there were software bugs. So I guess the 70s software was perfect. I don't know. Even though I was working in the most peripheral parts of this, I think that working in a system that was designed to be this fault tolerant influenced me in my view of how you design systems. So I often think about like how can we make the system run even though parts are malfunctioning. So yeah, fault tolerance to begin with is architectural. There is not a heck of a lot you as an individual developer can do to improve fault tolerance. Unfairly though, you as an individual developer can really ruin tolerance, fault tolerance. So that is unfair. If you divide your system into parts that can work in isolation and autonomously, then you can have a systems degradation, but still mostly work in a well-defined way. So you can allow parts to fail to save the whole. And I think this applies to a lot of software architecture. So you can, I'm coming to that later, you can choose to fail something that seems wrong, but keep the rest. But a key point is that you need to figure out how to get information back to you, the developer. And of course, in some systems, that is super difficult. And That's just the way it is. But in some systems, it's not really that hard. So if your device is networked, you can have some kind of call home mechanism or something that raises the awareness of the operator and say, hey, send this information back to the developers so that they can fix this problem. What if the problem is local? If you're certain that you found that the inconsistency you found you discovered it before too much damage is done on a system level, you can fail the offending part and save the rest of the system. So fail a transaction, drop the video stream. I work in video streaming. Shut down a board. Abort the file download. Who cares? Just restart it. But how sure are you? And these things are extraordinarily difficult to test. How do you test that you probably correctly react to a situation that you don't know what it will be? This is not easy. So, and a neat trick. If you're working on a Unix-like system, this is cool. If we find that we have this part of functionality that is inconsistent in a way that we can drop, just kill it and keep going. You can fork. On a Unix-like system, fork makes an identical copy of the process. So the fork returns twice, one in the parent process and one in the child process. And if the return value from fork is 0, then you're in the child process. So now I can log saying that something really bad happened, blah, blah, and call abort. Abort causes a core dump, which is enormously good for debugging. And then the parent process can force kill this broken functionality. Yeah, someone actually made slides about that. That is cool. A core file can be read in a debugger for post-mortem. So it will act as if you stopped on a breakpoint. And you can analyze the system, its state. You cannot step anything. You cannot run anything. But you can analyze everything in the process. So a colleague once described the core dump as the skid marks to the crash, which I guess is not completely wrong. And it's also the wreckage, by the way. One of the things that I found that is super useful, it doesn't work in all situations, but I have tiny RAM logs for pieces. So for example, I have written a number of networking protocols that you implement in terms of state machines. So depending on what message you receive, you go to some different state. So for each state machine, I have a RAM log. It can be just a std vector of strings. That is fine. So I log, whenever an event happens, I log what time is it, what state was I in, what was the stimulus, what state did I live in, and maybe some auxiliary information also. And if I get a core dump, I read it. In the debugger, I can find the offending state machine. I can read the sequence of events that led to this crash. And that is how I managed to solve a really, really weird situation. Or actually, it's not weird, but maybe I can be forgiven for not having handled this. So this communications protocol works with hardware acceleration, let's say. So when establishing a new connection, you do two things. You prepare the local hardware to accept to start working on the new network connection, and you also send a message to the neighbor node. You're gambling that the neighbor node will probably say, yes, sure, go. So when you receive the positive acknowledgement, you just say, start using the state that you have already that has already been set up. Except that I failed to properly handle the situation where it took longer to get the response from the local hardware than from the neighbor node across the network. So, yeah, we crashed. I got a core dump. I found the offending state machine. I read the small RAM log connected to that machine. I could see what happened, the whole sequence. And within minutes, literally within minutes, I had a reproduction of the problem in a unit test. Because I just had it in plain text, exactly the sequence of events that I didn't handle correctly. This is amazingly powerful. If you are not lucky enough to be in a system where you can force a core dump, you can at least, in these bad situations where you choose to terminate something, to cut off something, prune the tree of functionality, at least log the backtrace. This is part of the standard library now. It came in 23, didn't it? I think it came in 23. And the RAM log. Super useful. Make sure that this information comes back to you, the developer. And then you're good. You're going to fix this bug in no time. And I've gone way, way, way too fast. I'm sorry. You're going to have a lot of free time this afternoon. So, to summarize this, I don't think there are any generic right answers. I mean, by definition, you are in a wrong situation. You have a bug, and you have been exposed to the effects of this bug. So what do? Sacrifice execution to save data? Maybe. Continue running, doing the wrong thing. Maybe that is actually exactly what you should do. Revert to some kind of safe mode. I don't know. Probably a plethora of other possible things you can do. Please resist the temptation to sweep bugs under the rug. Please. If you must crash with actionable information so that you can actually do something, you can find the problem and you can fix it. If you just crash and say, oops, something went wrong and that is the only information you have, then sorry, not good. Make sure that there is a way for this information to reach the developer. In some kind of devices, that is not easy. But in some, it's very easy. It depends. Again, resilience is architectural. You can only do so much as an individual developer. You have to agree together on these things. And this is one I have made more than a few managers feel extremely uncomfortable about. Every bit of cleverness that you add to the system to keep it running, to save situations, is added complexity that makes the system more prone to bugs. And these clever things are super difficult to test. So don't try to be too clever here, to do something simple. So one thing that we do that is super useful, we have a completely separate process that just monitors for certain log entries and monitors for core dump files. And it runs completely separately from everything else, so it just notices that, oh, this happened. Better notify the operators and say, please send this back to the developers. The system software itself that does the work has no cleverness in it at all. This is reasonably safe, I think. Not 100% safe. But don't try to be super clever. Things like I mentioned with the AXE phone exchange, where you transfer work from one CPU to another, etc. This is super error-prone and super difficult to test, that you get it right in every conceivable situation. So don't try to be clever. Not more than you need to. And that was actually all I had to say. Thank you very much. Questions? Nobody dares to ask anything. All right, well,
User-facing bugs, end user, stupid users.
yeah.
Anything you change?
Can you give an example?
A certain beloved word processor hitting a unexpected situation mid-writing, and it comes up with, oops, something unhelpful.
Yeah, well, at least, so the example was a user-facing bug like my initial example with the word processor that it didn't crash, but maybe it should have. I don't know what is the right thing to do, except make bloody sure you don't ruin their files.
The other thing I'd like to see in those messages is rather than, oops,
Yeah,
an error number they can write down on a post-it.
yes.
To you about. Not words, but an identification number.
Yeah, so the suggestion was I agree, by the way, 100%. It's really horrible when a program shows a pop-up and just says, oops, something bad happened, and the only thing you can do is press OK. Like, it's much better if you gave at least some information, an error number, something. Specifically mentioned a short number that you can write down and contact your representatives with, contact support with, and say, this happened, what can I do? It's better to give at least some small thing. This, oops, is, I hate that. Sorry, what was that? Oh, not fan of the new Windows blue screen. No, no, that is not my preferred way. I mean, I can see that you don't want to overwhelm a non-technical user, and the vast majority of users are non-technical. But you should at least give it possible to access some more information. Okay, yeah, no, but at least I prefer a non-helpful message to having my data ruined. So there's that. Other questions? Yes, Victor.
Any opinionated takes on error handling in libraries versus application code? As in panic abort versus panic unwind, that kind of thing?
My take on error handling in libraries versus your own code. To begin with, I disagree with the choice of words error handling. This is trying to live with bugs. This is not error handling. This is difficult because how can you force a third-party library vendor to write code that conforms to your coding standards at work? You cannot do that. Of course, you cannot do that. It would be awesome if there was some standardized mechanism for this, like I don't know, contracts maybe. We'll see. I guess you could templatize on this, but I have not seen that done anywhere. It's hard. I don't know. I don't have an answer for you. Yes, Nicole?
So I've heard a lot of things about like how Erlang does this. For example, where you basically, from my understanding, I've never done anything with it. You basically have a bunch of processes, and then when stuff happens, you just kill them and restart them.
Yeah. My take on the Erlang approach, where you have a bazillion processes, and at the first hint of trouble, you just kill the process and restart it. I have no personal experience, so I don't know. My fear with this approach is that if the thing that caused your process to die was some state that is already in the database that you're reading from, so you're reading that back up when you start, then you essentially have a restart loop. But I don't know if that is something that actually happens. I have no idea. I think on a conceptual level, the idea is sound. You're sort of forced to develop your program into individual parts that runs autonomously, like I showed with the Ericsson telephone exchange example. So it's not the end of the world if something disappears and comes back up again. And that is great. But I don't have any more to say about that because I haven't worked with Erlang. Anyone else? All right. Have a good evening. By the way, here are, you can get the slides from this URL.